In this lecture, we'll look more at JavaScript prototypes, and we'll redesign our linked list class from earlier topics to make use of linkedList.prototype. Now, take a look at the linked list class here in the slide. This is a derivative of the linked list2.js file from an earlier lecture with some important changes. First, I've modified the add and the drop functions a little bit. Both now return an integer indicating how many items were added, which is trivially 1, or dropped, which is not so trivial, as that can be anywhere from 0 to every item in the list if all of them match val, the parameter to be dropped. We track the number of dropped items in the main for loop here. Now, second, I changed the name of the apply function to process to avoid confusion with another apply function in the JS library that we'll introduce in this lecture. And then third, drop is no longer recursive. I didn't want a distracting concept in there, and it's also hard to make the recursion count the number of dropped objects. The new non-recursive drop just keeps traversing even after dropping a node, looking for more nodes to drop and counting the number that it finds and drops. Now, question 1. Per usual, this is about JavaScript more than linked list logic, but also per usual, I still want you to understand the code. So, why do I only advance prior on line 27 instead of on each and every loop iteration? Doesn't it have to follow temp? Read the drop code carefully, and you may find it helpful to go back and review the first linked list version's non-recursive drop. And returning from a pause, prior has to remain one node behind temp, yeah, but it isn't necessary to change it when we delete the node at temp and then move temp to the next node, because in that case the node between prior and temp has been dropped, so prior is still one node behind temp. Now, with those details sorted out, let's look at the main change to linked list. Every function is in linked list prototype now, instead of directly in the linked list objects as it was in earlier examples. And per our recent discussion on prototypes, this should cause no difference in the behavior of the linked list objects. All the functions will work fine. And note that it's also more space efficient to do this. Without the prototype, each linked list object has to have its own copies of the function objects, though not separate copies of the code. That at least is not duplicated. With the prototype, each linked list object needs only the reference to its prototype, plus any object-specific data like head. And of course, we can adjust the function properties of all linked list objects together by tweaking the prototype. So it has several advantages. Now, such design is standard practice in professional JS, and from now on, your methods should go in the prototype unless there's a compelling reason to do otherwise. Now, we've also upgraded the test driver for linked lists. As you can see down here in the diagram, it's a separate file and loads both the linked list3.js, the file we were just reviewing. It loads that one. We'll discuss count linked list.js in a moment, but do note that the add and drop commands now report the number of items added or dropped. And note the addition of a count command, even though there was no node counting function in linked list. We are still expecting apparently to be able to call getCount to get the number of nodes. And so we come to count linked list. Now, this is a version of linked list that counts its nodes and reports the count via a function getCount, which you can see we call, at least in some cases, on line 16 of the test driver. Now, count linked list works by deriving from linked list, JavaScript style. On line 5 of the test driver, we create a count linked list for the second element of array lists. Now, this implies a constructor, so let's start there in file countLinkedList.js and see how you do inheritance in a language that has no traditional classes, just prototypes and constructors. Lines 1 through 4 are the countLinkedList constructor. It doesn't do much. Like any good derived class constructor, it defers all the base class initialization to the base class constructor. The only initialization it does itself is down here on line 3, initializing the new property count, which will be specific to countLinkedList objects. Now, line 2 needs careful explanation. Remember, we're in a call of new countLinkedList. That means an empty object was created and passed to us as our context object, referred to by this. We want to run the LinkedList constructor function on it to do linked list related setup, like setting head, for instance, to null. Question 1. How come we don't just write something like, say, this.LinkedList? Wouldn't that make our context object be the context object for the call of LinkedList? So there it is in the comment. Why not this.LinkedList? Turning from a pause, well, it would if it were allowed, but LinkedList is not a property of this. It's an empty object, remember, and so the statement is rejected for that reason. Flexibility in choosing this, the context object, is important in much of JS design. The same typeless freedom that lets a parameter or a variable be of any type also allows this to be of any type. And specifically, this does not have to point to an object that has the function in question as a property, or even has a prototype that does. The only requirement is that this have all the properties needed by the method. If it comes from a completely different constructor, well, that's fine. But you can't just pick a this via the syntax whatever I like dot whatever function. That syntax does require that whatever function be a property of whatever I like or of its prototype chain. Instead, you use the apply function, which is a property of every function object, including linked list. Now, the apply function calls back the function that it was called on, its context object, linked list in our example. For this callback, apply passes apply's first parameter, this in our example, as the context object. And if there's a second parameter, it passes as actual parameters the elements in that second parameter, which second parameter would be following this if it were there, which second parameter must be an array. If the second parameter is missing, as in our case, then no actual parameters are passed, only this parameter. So line 2 does what we were trying to do with this.LinkedList. It calls LinkedList with our this as the context object. Got all that? Think it through carefully, because almost all serious JS code makes use of apply, and we have some in-lecture questions on it coming up here. Question 3. Please translate the following in the notes: conventional function call into an apply call. You'll need to properly pass to apply the context object and the array of actual parameters. And I'll even drop a note up here in the slides so you can see that. That's what we're looking for. Do that with an apply. Coming back from a pause, what you need to write is s1.subster.apply, and then you're going to have to pass s1 as the context object, and then you're going to need an array for the actual parameters. So you still need the s1.subster because you have to get to the function, and it's a property of s1. But the apply call takes the place of the conventional function call, with the this parameter explicitly shown and the actual parameters jammed into an array. Okay, so question 4. Actually, I lied when I said you still needed s1.subster to get to the function. you can get to subster without any use of S1. Rephrase your answer using S1 only once as a parameter to apply. And do remember that S1 is a string, of course. And returning from a pause there, what you could have written instead, string dot prototype, a bit of a mess there, string dot prototype dot subster dot apply S134. Remember that almost all function properties are actually in the prototype, which is accessible via the constructor. Now, the apply function has a close relative, call. The two functions work exactly the same, except that call does not require parameters to go in an array, but instead lets you list them normally. So, for instance, I could have changed the apply call here to that. So after that long but important digression, we can now see that line 2 calls linked list on our count linked list object. But what prototype does our new list object get if it receives the attention of two different constructors? The prototype of whichever constructor was invoked by new, which is count linked list in our particular case here, right? Now, some JS references, by the way, will say that the constructor sets the prototype, but in truth, the constructor is just a function like any other. It wasn't declared with some constructor label or keyword, and it doesn't know that it's being called via new. It is really the new operator that sets up the prototype based on the prototype property of the function that you're calling it with. So, in summary, after the new count linked list call, we have an object with prototype set by count linked list, but whose data has been partially initialized by linked list. Now, what about its function properties? These come from count linked list prototype, of course. But as you can see, that prototype provides only the add and drop and get count function. It has no process method, despite the fact that we do expect to call process on a count linked list object in the test driver. What we'll do is make linked list prototype up here be the prototype of count linked list prototype, following the pattern we saw in the prior lecture, where derived class prototypes point upward to base class prototypes. Now, this will let us reuse linked lists prototype as much as possible, as the diagram shows. But how do we do that? We could write, for instance, count linked list dot prototype dot under proto equals linked list dot prototype, but this uses the deprecated proto notation. So instead, line 6 uses the object.create method to set up linked list prototype as count linked list dot prototypes prototype. This method creates a new empty object, but with the new object's prototype set by the parameter. Question 5. Assuming this prototype chain, what happens if I call process on a count linked list, given that process is not in the prototype for count linked list? Turning from a pause, well, it will call the linked list version as found in the linked list prototype. If it's not found in our prototype, JS looks at the next prototype up in the chain and calls the calls the process method from the linked list prototype. So any functions omitted from count linked lists prototype will automatically default to linked lists version. And that's exactly as it should be for a derived class. If you don't redefine a base class method with a derived one, then you get the base class version. Question 6. There is still a missing piece in the setup of count linked list dot prototype, a property it must have. Check the diagrams from the prior lecture if you need to figure out what property of the prototype is missing, and write a simple assignment to add it. Turning from a pause there, what we need is a constructor property. which is supposed to be part of any prototype. And we can add that by writing count linked list.prototype.constructor equals count list. Now, object.create does supply another way to accomplish this with a second parameter, but it requires a discussion on define property, which we haven't covered yet. The approach shown here will suffice for now. And we'll add that constructor property in the diagram here as well. Now, let's move on to the two functions add and drop, which are supplied in countLinkedList's prototype. These rely on their linked list versions to do much of the work. As you can see, they call the add and drop methods from linked list first via apply, and they save the result of those calls and then do their own value-added work of incrementing or decrementing the count property to reflect the number of nodes added, or in the case of drop, number of nodes removed. And they finally return that number themselves, as they're supposed to. Now, in any object-oriented language, it's quite common for a derived method to call the base version of the method to do most of the work, and then to add a bit of embellishment of its own. In Java, these first lines would be super calls, and in C++ they'd be linked list :add or linked list :drop calls. Calling base versions via apply is how you do this in JS. Question 7. Why couldn't those calls just be this.add val or this.drop val? The context object is a count linked list which has the necessary properties to work with linked list.add or .drop functions. Returning from a pause, well, because the add would follow the proto of its this, which is a count linked list, and would arrive back at the same add function. It would be an infinite recursion, in fact, if you did that, if you just wrote this.add. So we do need to do it explicitly by the call of apply. And finishing up the prototype, by the way, there's one entirely new function, getCount, that returns the count that the other two functions have maintained. This one is a simple addition to the prototype. It has no base version to call. A clear visual picture of prototype structures is essential to understanding and debugging JS. So go over this diagram and the prototype diagram from an earlier lecture, the prior one, until you can keep track of all this. And let's do one final point. Looking back at the test driver's implementation of the count command on lines 15 and 16, we see something sort of interesting. It checks to see if the list in question was constructed by countLinkedList, calling getCount if so, or just printing NA if not. Now, this constructor test is the analog of a list instance of countLinkedList expression, for instance, in Java. The constructor property is a good way to check the real type of an object. And then one last note that will appear in some of the LMQs as well. Let me quote from earlier in this very lecture. You use the apply function, which is a property of every function object, such as linked list. That's what I said. Question 8. That's a lie, in fact. Why is that a lie? If apply is not a property of the function object, like linked list, then what is it a property of, and why can we write linked list.apply? Returning from a pause, well, the answer should be a bit of a reflex by now. Apply is a property of linked list's prototype, not of linked list. But now constructors have prototypes, proto-properties too? Of course they do. It's hard to view a function as an object since it looks so code-like, but never forget that it is simply a normal object. Linked list and count linked list for that matter, are normal objects. They simply have a special added code property, plus that mysterious closure context I've mentioned earlier and we have yet to discuss. So what's the constructor for functions? Well, predictably, it is called function. It's actually a library constructor. And one may actually create a function object via this constructor. In fact, you can actually frame up some JS code in a string as the program runs and create a new function by passing that code to new function on the fly. Now, doing so is beyond the scope of this course, but you can bet we'll do it in a more advanced course at some point. For now, it's enough to know that function is the constructor of every JS object, of every JS function, and that the functions have proto-properties that contain a bunch of member functions like apply that deal with function objects. And be sure you understand the difference between a constructor function's prototype, its under proto-property, and its prototype property, which are regrettably not the same thing. Here's a little diagram of count linked lists, the function object, that may help. It doesn't show all properties, but it does show the under proto and the prototype properties. The former leads to function.prototype with its apply function and so forth. And the latter leads, of course, to the count linked list prototype that we just set up. Recall I said earlier that prototype was poorly named and should have been called model prototype. Count linked list.prototype is the prototype for objects constructed by count linked list. And it has functions like add and drop. Count linked list.under proto, by contrast, is the prototype for function objects and contains function properties like apply. And a final little in-lecture question on that. Fill in the equality check shown in the notes so that it's always true, assuming that f is some function and without using f in the blank. Returning from a pause, well, the answer is that object.getPrototype of f will, of course, always be equal to function.prototype. F gets its prototype from its constructor's prototype property, function constructor's prototype property, like any other object.